This is Lesson 18, Quadratic and Rational Inequalities. Now, we all know what an inequality is. It's a relationship where you have one side and the other side, and instead of having equals, as you have in an equation, between the two sides, you have less than or greater than, less than or equal to, or greater than or equal to. And what I'd like to do first is to discuss very briefly what a quadratic form means and what a rational form means, then talk about the meaning of the inequalities in this situation, and then do some representative examples, first of quadratic inequalities, then of rational inequalities, and finally show you an alternate method. So you'll have two methods of solving these kinds of problems. You can choose the one you like the best. At the end, I'll tell you which one I like the best, but I won't tell you that first because I don't want to spoil your opportunity to choose your own method. First of all, let's see. Let's go ahead and go to the easel and talk about quadratic and rational. Now, we've worked with quadratic equations and quadratic functions. Let's see, quadratic, we got it, that's a C. And that is of the form ax squared plus bx plus c. And when we're going to have a quadratic inequality, it's going to be that is less than 0, or is greater than 0, or less than or equal to 0, or greater than or equal to 0. So that's what a quadratic inequality looks like. How about a rational inequality? You know, we really haven't talked about rational functions. The word rational contains the word ratio. A rational number is a number which can be written as the ratio or the fraction where the numerator and denominator are both integers. Okay, so negative 1/2, 4/7, 5/3, negative 11/2 are all rational numbers. A rational equality would have a fraction whose numerator and denominator were polynomials, and then a less than or greater than. For example, you might have ax plus b over cx plus d is greater than 0. And that's a rational inequality. So these are the two kinds of inequalities we're going to solve. Hopefully you remember that when we solve inequalities, we don't get an answer like x equals 4, x equals 7, or any kind of answer like we got with quadratic equations or linear equations. We get a group, a family of answers, a whole area of answers. X is less than 12. X is greater than 7. Or perhaps we have an or situation. X is less than 2 or X is greater than 10. And sometimes we have a between situation. X, let's see, is between -3 and 5, including -3 and 5. That would be -3 is less than or equal to X is less than or equal to 5. But before we see how to solve these kind of inequalities, I want to talk about the meaning. Because so far, we had inequalities was like, x plus 2 is greater than 7, and we got the x on one side and the number on the other side, and we read the answer. But here, it's a little different. We're going to have to understand something. So let's go to the board and talk about the quadratic inequality. And what we're going to do with the quadratic inequality is to factor the quadratic equation, or the quadratic polynomial. Just as we saw, we could factor back, we talked about quadratic trinomials back in the lesson on factoring, which seems like years ago. And it could be, if you're watching this tape over a long period of time, it could be years ago, but probably not. Let's see. And let's say we had this factoring, this product of two binomials, for example, was greater than 0. What would that mean? How could you have two numbers, if you multiplied it, they were greater than 0? First of all, what does greater than 0 mean? It means a positive number. If I multiply two numbers and the answer is positive, that means that either both the numbers are positive or both the numbers are negative. Now, what opposite happens when I would have that quadratic inequality and factor the quadratic into two terms, and it would be less than 0. What does less than 0 mean? Well, that would mean that one of these is positive and one of these is negative, because less than 0 means a negative number. So the first one could be positive and the second one could be negative, or the first one is negative and the second one is positive. Let me say that again and listen for the conjunctions and or. The first one could be positive and the second one could be negative, or the first one could be negative and the second one could be positive. We'll use some symbology for or and it will be very important in our answers we get around to solving these inequalities. How about a rational inequality? I'll use the parentheses to represent some binomial, perhaps. We have a binomial divided by a binomial is greater than 0. What does that mean? Again, greater than 0 means positive. This is a positive fraction. That could be true if this was positive or greater than 0 and this was greater than 0, or they both were negative. This was less than 0 and that was less than 0. Of course, if we had the rational inequality that was a less than situation, the numerator could be positive and the denominator negative, or the numerator could be negative and the denominator could be positive. These are the ways we're going to solve this. By the way, you'll notice I didn't use any inequalities that have equals in it. And that shouldn't change too much except with one very special circumstance, which of course we'll have an example of later on in this lesson. So now let's go to the first visual. And that first visual shows us an inequality that's quadratic. X squared minus x minus 12 is greater than 0. We have factored the quadratic inequality. X minus 4 times x plus 3 is greater than 0. Again, if you forgot about factoring, go back to the lesson on factoring and review the factoring of a quadratic trinomial. The solution is underneath. You'll notice we have two sets of inequalities separated by a vertical line. That vertical line means or. We have one solution or the second solution. And we also have a comma between the two inequalities on each side. That comma should be read and. Both of those must be true. So let's take a look in the visual at those inequalities. The x minus 4 must be greater than 0, comma, which means and x plus 3 must be greater than 0. Both factors must be positive for the product to be greater than 0, to be positive. Or, on the right side, x minus 4 is less than 0 and x plus 3 is also less than 0. Both terms must be negative and the product is also positive. Okay, in the next visual, we solve. That is, x minus 4 is greater than 0 becomes x is greater than 4. Again, we're just solving simple inequalities. As we do more and more complex problems, we always go back to more simple things. When we're solving systems of equations with 2 or 3 variables, we always went back to solving an equation with 1 variable. Now we go back to solving simple inequalities in order to get solutions to more complex inequalities. Okay, and of course x plus 3 is greater than 0 yields x is greater than negative 3. So on the left-hand side we see that x is greater than 4 and x is greater than negative 3. Now, how do you say that more simply? X must be both greater than 4 and greater than negative 3. If a number is greater than negative 3, must it be greater than 4? And the answer is no. 0 is greater than negative 3. 0 certainly is not greater than 4. But what if a number was greater than 4? Would it be greater than negative 3? 5 is greater than 4. It's also greater than negative 3. So the simple way to write the answer is as pictured on the second line in the visual, x is greater than 4. Notice, a nice way to remember this is if you have an inequality with two parts and both parts have the greater than symbol, like it does here, then the answer will be x is greater than the greater of the two numbers. Since 4 is greater than negative 3, the answer to this is x is greater than 4. If that makes no sense, then use the first analysis I did, looking at which solution covers both of them. Or we go to the right side, the other possibilities, and here we have x is less than 4 and x is less than negative 3. And of course, you can be both less than 4 and less than negative 3, but you must be less than negative 3 to do that. In other words, if your number is less than 4, for example, 2 is less than 4, 2 is not less than negative 3. So our final answer is indicated on the bottom, is x is greater than 4 or x is less than negative 3. We could visualize this as on the graph. We could have a mark with a 0, or I should say an open circle at 4 and an open circle at negative 3. And then from 4 we'd have a line with an arrow pointing to the right. From negative 3 we have a line with an arrow pointing to the left. And that would be a graphical representation of our solution. I haven't done that here. We will look at some graphical things later on, and then we can talk more about that. But basically, our answer is x is greater than 4, or it's less than negative 3. There's two possible solution areas. What should we do now? We should, of course, check. How are we going to check? Remember, inequalities, we check an answer that should work, we check an answer that should not work, and see what happens. So in our next visual, we see that we've chosen to use 5 because 5 is greater than 4. It should work. We plug 5 into the original inequality, not into the factored part, but in the original, which was x squared, which of course would be 25, minus 5, minus 12, and that, of course, 25 minus 5 minus 12 is 8. 8 is certainly greater than 0. So 5, which should work, does. That's good. The next visual, we test 0. 0 should not work. Why not? Because 0 is not greater than 4, nor is 0 less than negative 3. In fact, it's between that. It's in the area that is not part of the solution. 0 squared is 0 minus 12 is negative 12. Is negative 12 greater than 0? Absolutely not. So 0, which should not work, did not work, and that's good. It's nice to know that. And the next visual shows us our final check. We're checking negative 4. Why did I select negative 4? Because negative 4 is less than negative 3. We replace x with negative 4, we get 16. Notice negative 4 squared is positive 16. Plus 4, because minus and negative 4 is plus 4, minus 12. That all turns out to be 8, and 8 is greater than 0. So the points that should work did. The point that shouldn't work, the 0, didn't work. We are convinced our solution is correct, and of course it is. Let's take a look at another example. The next visual has the inequality x squared plus 5x plus 4 is less than or equal to 0. There are two things different about this inequality. One is that it's less than rather than greater than. Also, it contains equals, which means we remember that if we have two numbers multiplied and they equal 0, then one or the other equals 0. So you'll notice that we factored the quadratic trinomial to x plus 4 times x plus 1, and we have our two possible solution areas. We have x plus 4 is less than or equal to 0, comma, which means and x plus 1 is greater than or equal to 0. This is highlighted on the third line. We also have x plus 4 is greater than or equal to 0, and x plus 4 is less than or equal to 0. In other words, either the first one is positive or 0, and the second one is negative or 0, or the first one is negative or 0, and the second one's positive or 0. One must be positive, the other must be negative to multiply and be a negative, or one or the other could be 0, since it could be equal to 0. Then we have solved each set of inequalities. On the left side, we get x is less than or equal to negative 4, and x is greater than or equal to negative 1. And you'll see the words no with an exclamation point. In other words, no! Well, why not? Why, what do you mean no? What does no mean? What it means is you can't do it. You can't have a number that is both less than negative 4 like -5, -6, but is also greater than -1, like 0. It's just impossible. So therefore, that solution is not a solution. You can't have that. On the other side, we have x is greater than or equal to -4, and x is less than or equal to -1. Can you have that? Can you think of a number that's both greater than or equal to -4 and less than or equal to -1? Well, of course. -4, -3, -2, -1, and all those numbers around there. In fact, we are between, and thus the answer is written as between. -4 is less than or equal to x is less than or equal to -1. Now, how are we going to check this? Well, let's check a point that should work. We need a number between -4 and -1. Let's try -3. -3 squared, again, we're going back to the original inequality. -3 squared is 9, plus a -15, plus 4. Well, that's -13, I'm sorry, it's 13 minus 15, which is -2, which is less than 0, so that checks. Let's try a number that should not work. -5 should not work, because -5 is not between -4 and -1. -5 squared is 25, minus 25 plus 4. That's 4. 4 is less than or equal to 0? No way. So -5 does not work, and of course it should not work. Let's try some number that's not in the area between -4 and -1, but is on the other side of -1. How about 0? 0 plus 0 plus 4 is 4. 4 is not less than 0. And of course, therefore, 0 does not check. So the two numbers that should not check don't. The two numbers that should check do. We're right. We're okay. Now, let's take a look at a rational inequality. The next visual shows us that we have x plus 2 over 4 minus 3x. Again, the ratio of two binomials is greater than or equal to 0. It's very important for us to remember what equal to 0 means. When is a fraction equal to 0? A fraction is equal to 0 if the numerator is 0 and the denominator is anything else except 0. We don't allow zeros in the denominator because you cannot divide by 0. Okay? Which means if you look carefully at the solutions, or the steps in a solution, on the second line, which is highlighted, we have x plus 2 is greater than or equal to 0. The numerator could be greater than 0, positive, or equal to 0. And the denominator must be, 4 minus 3x must be greater than 0. Notice that greater than symbol is in blue to emphasize it's not greater than or equal to. The denominator cannot be equal to 0. The numerator can be equal to 0, but not the denominator. And of course, the alternate possibility on the other side is x plus 2 is less than or equal to 0. The denominator is 0 or negative, and 4 minus 3x, the numerator, is strictly less than 0. And the solutions we get on the left side, we get x is greater than or equal to -2, and x is less than 4/3. Can a number be greater than or equal to -2 and less than 4/3? The best way to say yes is to give you an example, and a good example would be 0 or 1 or -1. Sure, that works. On the other hand, we have the solution on the other side is x is less than or equal to -2 and x is greater than 4/3. That is impossible. You can't be on two places at once, so notice again the no with the exclamation point to indicate this is not a solution. Thus, our solution is -2 is less than or equal to x is less than 4/3. And again in the solution, that less than is in blue to emphasize, although the original inequality has had greater than or equal to, we don't have any equals over there because that's due to the denominator, and the denominator cannot be equal to 0. That's our final solution. If we wanted to check it, we could check it the same way. I'll allow you to do that on your own and check a number in between, like for example 0, 1, it should work, 2 should not work, -3 should not work. But let's go ahead and go on to the next inequality. Okay? What is different about this inequality? Well, it's a rational inequality. This is the next visual. It's a rational inequality, 2x minus 1 over x plus 7, and this is a less than situation, less than 0. And again, if you have a situation less than 0, then you know that the numerator can be greater than 0 and the denominator less than 0, or the numerator could be greater than 0 and denominator less than 0. One's positive, the other's negative. And that's indicated in the solution method. As you see, you can go through the steps and you'll notice that the solution is -7 is less than x is less than a half. The other side doesn't work, so that's our final solution. You can check -8 shouldn't work and it will not. 1 should not work, it will not. -2 should work and it will. So again, if you're still a little behind, pause the tape, look at this solution, go through it. Try to do it on your own without peeking, but I'm not going to spend the time right now going through all of the steps because it's very similar to what we've done in the past. You should be able to do it. I'd like to spend the remaining time talking about an alternative method to solving quadratic and rational inequalities. This method is more visual, perhaps. Okay, and again, at the end, I will tell you which my choice is, but I'd like you to make your choice after you've seen this second method. So let's look at the next visual. The next visual has a quadratic inequality. X squared plus 3x minus 28 is greater than 0. What we're going to do here is we are going to solve the equation x squared plus 3x minus 28 equals 0. And we're going to solve it. We could use the quadratic formula. We could, no question about that, but these problems generally can be factored since one of the ways to do this is to factor. So I went ahead and factored x plus 7 times x minus 4 equals 0. And then, if you remember, a number of lessons ago, we discussed solving quadratics by factoring. And I said then, it's probably the easiest way. It's even easier than the quadratic formula once you see how to factor it. The quadratic formula is nice because it always works. And so here we have x equals -7 and x equals 4. And what I've done is I've drawn the number line, 0 indicated, and I have 4 and -7, the two solutions to the equation indicated on the number line. If we look at the next visual, we can see we have the number line. Above it is our inequality in factored form. X plus 7 times x minus 4 is greater than 0. And then what I've done is I've taken 3 points. 1 point below -7, that is -8, which is indicated. 1 point between -7 and 4, and that was -5. And then 1 point to the right of 4, which was 5. And we're going to test these points. And if in turns -8 works, then we'll know anything to the left of -7 will work. If -5 works, then anything between -7 and 4 will work. If +5 works, then anything to the right of 4 will work. Because we know once we test one point, the whole area is okay. So we're testing a point to the left of the leftmost number, the -7, between the two numbers, and to the right of the rightmost number, which of course is to the right of 4. And those are indicated. We have x equals -8. That line is highlighted. You can see that when we plug -8 into the factored form, and it's a lot easier to plug numbers into the factored form, because we're not interested in what the answer is numerically. We're only interested, is it positive or is it negative? So we have -1 times -12, which is positive. The fact that it's 12 is irrelevant. It's positive, and therefore it's greater than 0. Yes, because our original inequality was greater than 0. When we test x equals -5, we get 2 times -9, which is a positive times a negative is not greater than 0, and therefore -5 is not a solution to this inequality. The word no is written there. On the next line, we have x equals 5. That's highlighted now. And we have 12 times 1, which again is positive. And yes, that's a solution. So we know that to the left of -7 works because -8 worked, and to the right of 4 works because 5 works. And thus our solution, x is less than -7 or x is greater than 4. The kind of neat thing about this is we really don't have to check it. Well, we could if you don't believe in your factoring. because if you factored incorrectly, since we used a factored form to check the points. But assuming we did that correctly, in effect, we've solved by checking. It's kind of a nice thing. Let's take a look at the next visual. This visual has a rational inequality. 2x minus 5 over x minus 1 is less than 0. Remember now, a rational inequality, the numerator is positive and the denominator is negative, will give us less than 0, a negative answer. Or if the numerator is negative and the denominator is positive, so we have two possible solutions. Except we are not going to do it that way. We're going to simply take and set the rational function, the 2x minus 5 over x minus 1, equal to 0. Equal to 0. And what we're going to say actually is 2x minus 5 equals 0, and the denominator, x minus 1, equals 0. You say, wait a second. You said the denominator can't be 0. You're right, it can't. And because it can't be 0, it turns out that's a very interesting place to look to the right and to look to the left. Because in this method, we're going to find points not as solutions, but to look to the left and look to the right, or look in between. So let's go ahead and set the numerator equal to 0, the denominator equal to 0, and solve. And of course, the solutions to those two equations are quite simple. They go back to one of our earliest lessons. X equals 5 halves, x equals 1. And below on this visual, we see the number line, 0 indicated. I always like to show 0, just so I make sure my positive numbers are on the right side of 0 and my negative numbers are on the left side of 0. And the two solutions to our two simple equations, 1 and 5 halves. And in the next and last visual, we see the number line, the 0, 1, and 5 halves shown, but also in dark blue, I've selected three numbers. Negative 1, which of course is to the left of 1, 2, which is between 1 and 5 halves, and 3, which is to the right of 5 halves. Notice we have the original inequality, 2x minus 5 over x minus 1 is less than 0. And now we're going to test those three numbers. First, we test x equals negative 1. Negative 7 over negative 2 is a positive number which is not less than 0. Let's see, the next we try x equals 2. 2 is between the 1 and 5 halves. Negative 1 over 1, that is when we plug 2 into the original inequality, we get negative 1 over 1. That is a negative number. Yes, that is a solution. X equals 3, a number to the right of 5 halves. We plug that in, and what happens? We get 1 over 2. 1/2, being a positive number, is not less than 0. So we have that negative 1 didn't work, 2 worked, and 3 didn't work. What does that mean? What would you say the solution to this problem is? Well, the solution is that our answer lies between 1 and 5 halves. So that would mean that 1 is less than x is less than 5 halves would be the correct solution. Any number between 1 and 5 halves would be the only numbers that would work in the original inequality. Now, we've come to a point, I've shown you both methods. Which method do you think I like best? I like this method best. And the reason is very simple. It's visual. It's easy. We're involved with solving equations, which is generally easier than solving inequalities. But if you like all the stuff that went on in the first half of this tape, where we showed you how to solve the inequalities, or if your teacher demands that you do it that way, that's fine. It certainly is a valid way to do it. But I just think that by solving equations and testing points, we have a much better solution. By the way, those of you who are planning to take calculus will use this kind of method in some very important problems in the first semester of calculus. But we'll worry about that in another series of tapes, perhaps. This concludes this lesson. In our next lesson, 19, we'll be talking about the division of polynomials, something we skipped early on when we talked about addition, subtraction, multiplication, because now we can finally learn to divide polynomials. We'll see you in Lesson 19.